Good morning, everyone. People are still joining, so we'll start the webinar at 11:05 sharp. I'm again repeating, people are still joining. We'll start the webinar at 11:05 sharp. Hello, everyone. Good morning. My name is Vatan Sharma. Can someone please confirm that my voice is audible or not? You can write it in questions chat box. Yes, yeah, I got the confirmation. So I welcome you all on the behalf of Midas IT for the webinar series that is finite element modeling and analysis of hydropower structures, presented by Chetan Agrawal sir. This is the seventh session, this is the seventh session of the webinar series, which is on dynamic analysis of for the design basis earthquakes, DBE earthquake, and going through the relevant clauses, which is like from the code, like USAC manual EM6051 for the analysis of gravity dam. So before going towards today's content, I would like to request Chetan sir to provide a brief recap of the previous sessions for the audience. So I'm making you presenter, sir. So, sir, you are presenter now. You are not audible, sir. Yes. Hello. Hello. We're not able to hear you, sir.
Am I audible now?
Yes, sir. Yes, sir. Now you are audible.
Okay, my screen is visible.
Yes, sir. Yes, sir.
Okay, so welcome everybody to this session. Hope you are learning something from these webinars. So in last session, we had analyzed our NOA block, deepest NOA block for the static loads, and then I had taken that image of that 3D model into my Excel sheet. And for the stability analysis, we need raft properties also, area of raft, moment of inertia. And for that, I had taken my model to AutoCAD, and from there, I had computed the CGs of the inclined portion of this raft. Otherwise, it's slightly complicated, slightly difficult, and we make, I mean, we may be committing some error while evaluating the CGs manually. But if you are confident, you can of course can compute it manually for this inclined portion. So I have used AutoCAD for evaluating the CGs. Then from using this mass prop command, and then taking it to this my Excel sheet, because I'll be needing these CGs and moment of inertias for computing the base pressures. As you know, that base pressures at various corners are P by A plus minus mx over zx plus minus my over zy. You know this, and z you can compute from the moment of inertia about that axis. And what divide by the distance from the extreme fiber. So moment of inertias and everything I computed in this Excel sheet to get the base pressures. Then after that, I had gone through the various loading conditions as per the codal provisions, usual, unusual, extreme loading conditions, and then I compiled the results, and then I checked the stability for the construction conditions and the normal operating condition. Uh, So this was for the normal operating condition, considering the various applicable loads. And then for seismic condition, then I compiled all the results. We had, I mean, for the uplift, we had modeled that water element. I think that was in the last session. And then I set up my model for the dynamic analysis For dynamic analysis, I had modeled the foundation. Foundation it should be modeled. That should be enough. That extent of foundation should be enough so that the prominent deformation bulbs are within that our modeled foundation. So I had considered the foundation along the depth equivalent to the height of the dam, and on each side also equivalent to the height of the dam. That means almost 2 times the height of the dam I had modeled along the flow, the extent of that. uh, that should be initially that should be considered enough so that the prominent deformation bulbs are within that limit, within that modeled ground. So we'll check that in today's session, whether our prominent deformation bulbs are within that ground or not. Then I had provided the free feed boundaries. Either we can provide the free feed boundaries or the absorbing boundaries on the side faces, so that the seismic waves are not reflected back and affect our structure. To get a correct structural response, I had applied these free field boundaries. Free field boundaries will absorb all the seismic waves, and it will not reflect back the seismic forces back to the structure. Okay, so you can provide absorbing boundaries, viscous dampers also on the edges, and in the bottom I had provided complete restraint at the bottom. It is as per USAC Engineering Manual 6051. They had also done in a similar way. Okay, then I had set up my model. I had defined all the parameters required for the dynamic analysis, and I applied the loads. Okay, and in this session, we'll be analyzing our dam for DB, design basis earthquake only, and for that we'll get the reactions, and then we'll combine those reactions with the self weight and other loads to check the stability against sliding for the DB. Okay, so over to you, Vatan. Vatan, this is it from my side for the
Thank you,
recap.
sir. Thank you for the briefing, sir. Okay. Okay, so this is the briefing. Now we are moving towards today's content. So this is the webinar. Okay, just a minute.
Of the webinar, I'll start from where I left in the previous session. So we have set up our model for the dynamic analysis. Okay, so we had this analysis case for DB, linear time history and direct analysis. I'll start solving it, and then meanwhile we will be discussing the codal provisions, what we want to achieve from this analysis, the dynamic analysis. We'll be discussing that aspect. Okay, let it start first. So it will take quite some time for the analysis. For each cycle it will analyze. Okay, let's wait for 1 or 2 minutes so that the analysis for each step starts. Yes, it is running fine. So it's fine. Okay, let's go to the code then. Okay, so I'll be considering provisions of Engineering Manual 1102-6051, 22 December 2003. This USAC Engineering Manual for the dynamic analysis. Okay, let's go through this code. So the purpose, scope, you can read it. So it's not of okay. We'll go through all the relevant code clauses. Most of the relevant clauses, whatever we can go through. So the overview Overview of seismic design and evaluation procedure. Seismic design and evaluation of hydraulic structures generally consists of following steps: selection of design or evaluation of earthquakes. We have evaluated the earthquakes. Okay, we have that ground motion history. Seismic agency will do that. Selection of method of analysis. We carried out pseudostatic analysis first, and then we jump to the time history analysis and development of acceleration time histories that is already available with us with some other agencies. Definition of load combinations that we have considered as per IS 6512. It is almost similar to engineering manual 2200. Okay, then development of structural model. We are performing three-dimensional analysis, material properties, and damping. We have assigned. We are not considering any damping for the foundation. We are considering massless foundation, and for concrete we have already provided. And selection of numerical analysis procedure. We are using direct time history method for numerical analysis. We'll go through the difference later on. Okay, determination of performance and probable level of damage. So this we are doing this analysis to determine this performance and probable level of damage. Okay, so there are criteria for this. Okay, for this performance and probable level of damage. So design earthquake criteria, design and safety evaluation. Earthquakes are for concrete hydraulic structures are the operating basis earthquake or design basis earthquake, and maximum design earthquake is required. Okay, you can go through this code. So then OB design basis earthquake is defined in this as an earthquake that can reasonably be expected to occur within the service life of the project, that is with a 50% probability of accidents during the service life. This corresponds to return period of 144 years for a project of service life of 100 years. Okay, see there are attenuation relationship, logarithmic relationship for evaluating our response spectra. Okay, we can have these 144 years spectrum acceleration versus time curves. There is an example in this code. Okay, you can please go through this code. There is an example for how to evaluate this one. Most of the agencies are following the similar procedure. So then maximum design earthquake is the maximum level of ground motion for which the structure is designed or evaluated. So whatever has been recorded in last 1000, whatever is the maximum earthquake recorded, that normally we consider. Okay, well, seismic seismologist or their seismic expert, they will provide these time histories to us. For critical structures, requires the MDE to be set to equal maximum credible earthquake. Okay, that is MDE, MC. We are critical structures are defined as structures whose failure during or immediately following an earthquake could result in loss of life, like dam, of course. The MC is defined as the greatest earthquake that can reasonably be expected to generate by specific source. Okay, on the basis of seismological and geological evidences. Okay, so you can have a look at it. So for MD, we can consider 100 years probability of accidents. For DB, 50 years. So for and return period of 950 years. DB, 144 years. So this is there. Then method of analysis. Seismic analysis of concrete hydraulic structure whenever possible should start with the simplified method and progress to more refined analysis as needed. A simplified analysis establish a baseline for comparison with the refined analysis, as well as providing a practical method to determine if seismic loading controls the design. We have already carried out this simplistic seismic coefficient method for the analysis, and thereby offers useful information for making decision about how to allocate resources. In some cases, it may also provide a preliminary indication the parameter significant to the structural purpose. The simplified methods for computation of stresses and section forces consists of pseudostatic or single mode response spectrum analysis. See, we have carried out this pseudostatic analysis considering the seismic coefficient response spectrum. Actually, this is a enhancement of this pseudostatic method only. So response spectrum, we can plot the curve between the time period of any structure and the acceleration, the maximum as response of that structure in terms of its acceleration, depending on its damping properties. Like for concrete, considering 5% damping, and the structural time period based on its shape, height, whatever time period, we can have the spectral acceleration of that. We can plot a curve between that. So it will give the maximum response at particular time period, and that will define the boundary condition for in the frequency domain for that structure. But we are not simulating the ground motion for each time cycle. We are not evaluating the behavior of the structure. So here also then this this is called response spectra method. I mean, in response spectra method also the mode shapes of the structure defines the actually this boundary constraint. Okay, so it will depend on the how many number of modes we are selecting. We should try that maximum masses in the structure should participate. So we should have enough modes for that. So this is also, I mean, this is dependent on the this response spectrum mode superposition method is dependent on the number of modes, and it will give the maximum responses. It is not the accurate method for the analysis. Okay, oh, where we have the simple. Okay, let's see. Okay, so we are not doing this response spectrum analysis. We are performing the straight away time history analysis. The simplified method for sliding and rotational stability during earthquake excitation is usually based on the seismic coefficient method. So this we have already carried out. Sliding and rotational stability means base pressures we have to check. So for A and B condition, I mean the construction and normal operating condition, our resultant should lie within the base. Rotation should not be, movement should not be such that we have tension on in the base, that we have already checked. And for other load cases also we have considered. The permanent sliding displacement may be computed by a Newmark's rigid block analysis, as I have told you in the previous session. So this is more applicable for the what you call earthen dams, rock fill dam, where there can be a sliding between the different layers of the material. Okay, for concrete gravity dam, stresses are more important. I mean, we'll come to the DCR and cumulative inelastic duration criteria later on for concrete gravity dam or its numerator. The response spectrum mode superposition, you can read it. The response spectrum, we haven't done. Finally, I'll come here. The time history method of analysis is used to compute deformation, stresses, and section forces more accurately by considering the time-dependent nature of dynamic response to the earthquake and ground motion. We actually simulate the shaking of the ground here in time history analysis. This method also better represents the foundation structure and fluid structure interaction effects. See, foundation structure, of course, we have modeled. Fluid structure actually, Midas now has that sloshing material, inbuilt sloshing material, but I haven't used. I have still used Westergaard's added mass approach for fluid structure interaction. Okay. So simplified procedures we have gone through, and its stability, whatever. You please go through it. Okay. And for stability criteria, just go through engineering manual to 2200. Okay. Then acceleration, how to develop these time history acceleration input motions. So please go through it. It's not of much use. We already have this. Seismic experts will do this. Now to concrete gravity dams. Let's read this. Relative long and straight concrete gravity dam built as independent monolith separated by a transverse joint may be idealized using a 2D finite element model, including the foundation rock and impounded water. The 2D dam water foundation model, usually of the tallest cross section, may be analyzed. Analyzing the tallest model, but our shape is not uniform. We have a slope there, and we have galleries, a lot of stuff. So our CGs of load are not at the center of the raft. So 2D analysis is not a good approach for the NOF blocks like ours. So we are doing a 3D analysis for this. Okay, so please read this. Then curved, we don't have curved gravity dam, we don't have concrete RC gravity dam. Inlet, you can read this. 3D analysis of support towers. Okay. Okay, material properties. Okay, so see in frequency domain, when we are carrying out the dynamic analysis, we can increase our concrete properties, material. I mean, we can increase the modulus of elasticity of concrete by 20 to 30%. It is again dependent on the test results for dynamic loading. So uh, from the test results, we can get the dynamic modulus of elasticity. So it is normally 20 to 30% higher than the static modulus, but conservatively I have used the same static modulus of elasticity. I could have increased that. That would have reduced the stresses. Anyways, so next, the foundation properties, foundation rock properties for use in structural analysis include shear strength and rock mass modulus of deformation. A procedure for estimating shear strength is this. Okay, so you can have a look at it. Foundation soil properties. Okay, we have sound rock here. No damping. Please go through this damping. Okay, now numerical analysis procedure. Okay, we are doing this. We are performing this. Okay, we'll straight away jump to this one. Okay, so let's see the status of our analysis. Still increment is up to 182, so it has to go up to 800. Okay, so we have two types of time history analysis. Okay, first is mode superposition method. In linear response analysis, the mode superposition technique can be used to uncouple the system equation of motion so that the dynamic response can be obtained separately for each mode of vibration. That means mode of vibration will, I mean, define the boundary condition for this method. So number of modes are important here for mode superposition method, and then superimpose for all significant modes to obtain the total response. This way, the step-by-step time integration in one above is applied separately to number of independent single degree of freedom equations, and then the resulting model response histories are superimposed to compute the total response of the structure. The main effort in this method includes computation of eigenvalue problems, followed by the modal coordinate for eigenvalues we carry out for computing the frequencies and time period of each mode coordinate transformation to uncouple. So we have to carry out these eigenvalue analysis if we want this mode superposition method, modal time history. It is important to note that equation of motion will be uncoupled only if the damping can be represented by a mass proportional and stiffness proportional matrix, damping matrix known as Rayleigh damping. So it is important for this mode superposition, this Rayleigh damping. Okay, the Rayleigh damping is suitable when the damping mechanism is disturbed rather than uniformly throughout the structure. Okay, when it is damping mechanism is disturbed, but in our case we have considered zero damping for the founding material. It is not disturbed, so it is not suitable for our case. Okay, so then let's see the direct step. But in this method, the step-by-step integration is applied directly to the original equation of motion. You know, equation of motion, so that is force, internal force is equal to mass into single derivative of deformation, that is acceleration, that is mass into acceleration plus damping into sorry, double derivative of mass into double derivative of deformation, that is mass into acceleration, then damping into single derivative of deformation, that is damping into velocity, then the stiffness into deformation. Okay, so that is the equation, original equation of, with no need to modal coordinate transformation to uncouple them. So we don't need actually mode shapes for direct step-by-step methods. Okay, so every mass will participate for each cycle. Okay, whatever constraints we have provided in the model, that will be considered as a boundary condition for that particular model. Okay, instead of mode shapes. Thus there is no need to obtain natural mode shapes and frequency or to limit damping to the proportional type. So we don't have to do this Rayleigh damping proportional mechanism, we don't have to use. Okay, the method can be used for both linear and non-linear response analysis. So we'll be doing the linear time history analysis here. So then analysis, you can have a look at it. The damage criteria will come to gravity dams. So, okay, the dam response to maximum design earthquake MDE is considered to be within the linear elastic range of behavior if the computed stress demand capacity ratio are less than or equal to 1. the level of nonlinear response or cracking is considered acceptable if demand capacity ratio are less than 2. That means what is demand capacity ratio? It is the induced tensile stress divided by the allowable tensile stress. If it is 1, that means our gravity dam is behaving linearly, our gravity dam is perfectly safe. So even up to say 2 also, that means if the induced tensile stresses are 2, then also we can consider it to be safe. So we don't have to do nonlinear analysis. But if it exceeds 2, then we have to check the overstress region. I mean, we have to carry out the nonlinear analysis, but there is a criteria for that also, that overstress stress regions are limited to 15%. If the overstress stress regions are more than 15%, that means if the DCR is more than 2 in more than 15% of dam surface area, then we have to check the cumulative duration of stress exertions, in how much, in time cycles, in what time cycles, and up to how much duration those are exceeding this value of 2. Okay, for one particular node, say in a dam. So some and one particular time cycle, maybe some higher tensile stress, higher than the 2 times, more than 2 times higher than the allowable tensile stress is induced. Maybe in another cycle it is reduced again to less than the allowable. Okay, that we have to check how much, I mean, duration it is overstressed, that particular node. If it is so we have to plot a curve. So that curve is in 4:2 figure. So if say for concrete gravity dam we consider I mean up to 0.3 seconds, if and for 2 the zero, I'll show you the curve, then you can understand that better. We'll go through that. Okay, so we have to check these 2 criteria. First is DCR, demand capacity ratio, we have to check for. Okay, and then cumulative inelastic duration we have to check, cumulative duration of stress exertions. Okay, then so actually only these 2 criteria we have to fulfill for the concrete gravity dams. You can go through it, whatever is mentioned here. So I'll straight away come to that. Curve. Okay, so these are the criteria for various structures. Okay, okay, so I have used this Westergaard added mass approach for hydrodynamic force. Okay, instead of modeling water. Straight away. So equation of motion, as I was telling you. So this is the one. Force, the equation of motion equilibrium of reactive force is given by this: mass into double derivative of deformation, damping into single derivative of deformation, and stiffness into deformation. Okay, you can go through it. So this is not of, so yeah, this is, so here in this chapter you, okay. Next, allowable tensile strength of plain concrete. That is a big issue actually for normal when we design it for flexural member. Considering limit state or working stress method, we don't consider any tensile strength of concrete. That tension is taken by their reinforcement only. But for plain concrete, how much strength should be there? So for reinforced concrete structures also, with the reinforcement, there are provisions in various codes that with the reinforcement, the RCC section tensile stresses should not exceed certain limits. For say for direct tension or for flexural tension, it is say 0.7 square root of FCK, where FCK is the 28-day cube strength, and for direct tension it is about I think FCK by 7, I think. So for say M25, for direct tension it is about 3 MPa. Okay, no, yes, about 3 MPa. Okay, but for plain concrete, in in most of the codes, we don't find the allowable tensile stress of plain concrete. All the codes are mostly codes are for flexural members where the reinforcement take all the tensions. For concrete gravity dam, where we don't provide any reinforcement on the upstream or downstream faces, uh, we we can have a higher tensile strength than that what is mentioned in for the flexural members. Actually, in some of the literature you will find so the plain concrete has tensile strength of about FCK by 40. Okay, say if it is M25 concrete, 25 by 40 is about 0.6 MPa is the strength of plain concrete. We can consider that. Okay, but for in frequency domain, this strength is is much higher. So we use Raphael's formula for that. This is the Raphael's formula. This is Ft into 1.7 times of Fc raised to power 2 by 3. The tensile strength plain concrete is computed for DCR is obtained from uniaxial splitting tension test for this. So this, if you apply this, no, you will have a very high tensile strength. So, and if you compute your uh, bending moments in your normal building beams and slabs, and you will, if you compute the stress there, M by Z, tensile stress there, okay, you will find that those stresses are, lesser than this many times, most of the times. Sometimes it may be larger also, but most of the times those stresses are lesser than this. So that means in our building columns and building slabs and beams, we don't require any reinforcement if we consider this tensile strength. This tensile strength will be higher. It's in the range of 2 MPa or something. Okay. So this FCK by 40 is more appropriate, 0.5 or 0.6 MPa tensile strength for plain concrete. But for the static analysis, for dynamic analysis, consider this. Okay, Raphael's formula for DCR of 2, this will be multiplied by 2. So this is what has been mentioned. So DCR of reinforced concrete hydraulic structures intake defined as the ratio of section force demand to the section force capacity is taken as, so these are for the reinforced concrete structure. So we are performing our analysis for concrete gravity dam. Okay, let's see here. Please go through this explanation. So I'll just quickly go through this. Okay, say as we have seen earlier that demand capacity ratio is not the only criteria that our dam may fail. Okay, so see, DCR, it can exceed 1, the linear limit. Okay, it can even exceed 2 also in some of the cases. So if it exceeds 1, that means it is exceeding the allowable limit of allowable tensile limit of the concrete. Okay, so and see, I'll come to this. So this is the cumulative inelastic duration versus the demand capacity ratio plot. So we have to evaluate the demand capacity up to how much time there is the accidents of these stress exertions. Okay, uh, say say it refers to the uh, uh, okay, for example, cumulative duration of 0.4 second at DCR1 indicates that total duration of stress exertions above the tensile strength of the concrete. So that means up to 0.4 seconds in the entire time history what we have analyzed, that particular node has exceeded the DCR of 1. Okay, so for DCR of 2, we consider it as a 0. Said it, the node should not exceed, and your node should not attain this 2, more than 2. Okay, so it should be 0. It shouldn't have that high stressed higher stress, I mean 2 times the allowable tensile stress for the entire duration of the ground motion time history. If it exceeds that, we have to perform a non-linear analysis. Okay, and see, for concrete gravity dams, as it is a for cantilever, so I mean it's like a cantilever. I mean its deformation is as per the cantilever mechanism. Instead of 0.4, we normally consider it as 0.3. I mean, for a particular node, the stress exertion should not exceed this 0.3 seconds. Okay, for entire time cycle. Okay, for DCR of 1. Okay, so we'll be going through it. Okay, so I mean how to obtain these, the cumulative inelastic duration that can be obtained approximately by multiplying the number of stress point exceeding a certain stress level by the analysis time step. The higher the cumulative duration, the higher is the possibility of more damage. We can actually mm, sort out our data from higher DCR to lower DCR, and then we can check which nodes are for particular node of which in which time cycle time period those that node is exceeding the DCR of 1 or 2. Okay, so we'll be doing that while performing the stress analysis. Let's see how. So still it is processing. So okay, what else? So for concrete gravity dam, okay, so this is for concrete gravity dam. The demand capacity ratio is for concrete. So we consider cumulative inelastic duration of 0.3 here. If the cumulative inelastic duration exceeds 0.3 in entire ground motion time history cycle, but where we are analyzing for what we are analyzing, if it exceeds that, we have to go in this non-linear range. Actually, new I-code guidelines, it says that for all new dams, we should not allow our dam to go beyond this region, and any node of our dam to go beyond this region. Okay, old dams we can't help. I mean, for retrofitting, okay, for rehabilitation, we have to analyze those dams, and if it exceeds this limit, we have to perform nonlinear analysis and suggest some strengthening measures. But for new dams, if it exceeds this limit, we have to provide more concrete. We have to make each and every node of our dam, every I mean location of our dam within the allowable tensile stress limit. Okay, 1. Okay, so this is dynamic apparent tensile strength that is computed by the Raphael's formula, that is quite high. Okay, so performance evaluation or displacement histories, we'll plot displacement histories. Okay, this should be dam is maintained. Okay, principal stresses we will obtain. Okay, and demand capacity ratio time histories for critical. So this is more applicable for the arch dams. What else? Is there anything else of our interest here? These are for intake towers. Okay, and these are intake towers are flexural members. So these are nothing but your bending moment and axial force interaction curves. Okay, to check how much reinforcement is required. Okay. Okay, so we are not very interested in these examples. I mean, these clause. So I think for concrete gravity dam, only we have to check the stresses and check the DCR, and then So this is the example of a finite element model of a dam. This is a 2D analysis they have carried out. See here, splitting tensile stress of 2.5 MPa and 3.72 MPa. Okay, actually, as per Rafael's. So these are very, very high. Okay, so you will find these sort of stresses in normally M by Z, normally in your house beams and slabs, in columns also. So no need of reinforcement there if we go by this. Okay, so this is applicable only for the dynamic analysis. Just have a look at it. So then for this conclusion, they have displacement time histories have been plotted. Okay, so they have also not used relic damping. How do I know that? If relic damping they have used, some mass proportional and stiffness proportional would have been there, so it would have not been symmetric about this line. It would have gone something like this. Okay, so then accelerations, displacement, acceleration, stress, time curve we will also plot. Okay, okay, so we'll plot these stresses, principal stresses in our 3D model. We will just have a look at it. We'll consider these stresses in our 3D model. Earthquake ground motions. Okay. So this is for arch dam. Example of arch dam. I mean, for various structures, the procedure is same. Okay, some criteria may be different because see, arch dam again will provide some reinforcement. Towers will provide reinforcement. Flexure is there. For concrete gravity dam, there won't be any flexural reinforcement. So that has to be stabilized by the gravity loads. Okay, so various for piles, they have specified some criteria. Okay. Please go through this code. So let's come back to our analysis. So it's still running. It takes some time. Meanwhile, let's see our sheet. Okay, what I'll do, say A, B, C, these are all static condition, D condition. What I'll do, for each time cycle, I'll be computing the sum total of vertical force and the sliding force, and okay, then add it. Say if it is a D condition, add it with the vertical loads. Say in D condition only self weight will be there. Okay, and so I'll add that particular load here with the response I get from the this time history analysis. Similarly for sliding also. Sliding actually in D condition, in construction complete condition, the sliding is due to earthquake force only, so nothing will be added here. And then the factor of safety I'll evaluate considering these factors only. So in some of the cycles, when the acceleration is 0, you will find infinite factor of safety. So I have programmed it like this. So if it is sliding forces not equal to 0 only, then it will compute this factor of safety. Otherwise it will keep 100. Okay, otherwise it would have shown divide by 0. Okay, so 100. So that's so that I have the some figures for factor of safeties. So for each time cycle it is computed. So I have, okay, say for load condition. Okay, let's see load condition E, then I'll show you how I'll compile these loads. Okay, for each time cycle again, vertical for dB reaction I'll consider, then vertical forces here, self weight, then we will have weight of water and weight of normal tailwater level and upstream tailwater level. Then we have to subtract the uplift that I'll do for getting the vertical reaction, and similarly for sliding I'll add uh, the force due to upstream water pressure, silt load, and I'll subtract this normal tailwater level, this T11 and hydrodynamic force. As I have not modeled the water, I'll add it from my from this data which I have compiled, okay, and then evaluate the factor of safeties. So how to compile these results? So I have these reactions with me. So I'll get the reactions for each node. I mean each node where the restraints are applied, where the supports are applied, okay. Uh, so for each time cycle, say for 0.02 time step, whatever the time step, I'll get reaction on each node. Then I'll sum total it, okay, sum it, and then I can take it to the respective sheet D, E, G, whatever. Okay, similarly for vertical reactions also, I'll compile it in similar way, okay, and then sum it for all the time cycles. So that way I can find out the sliding force as well as the vertical force for the time history for various time steps of time history, and then I can plot this factor of safety versus time period time history, okay, like it has been done here. Okay, so factor of safety of 1, if it is all the factor of safeties are above 1, that means our dam is safe for E condition. Okay, see, we have areas C5 values with us, I mean 5 value with us. So here it seems to be some factor of safety is lesser than 1, but it's not of, I mean, for this case we'll get the results after the analysis is completed, so it's still 642. Okay, I'll resume the recording after it is completed, and then while it is computing, I'll just put off the recording. I'll come back again. So the analysis has been completed. Okay, so before seeing the result, let's go to the time history data. Okay, so horizontal dB. See, for the initial few seconds, initial few time steps, it's almost 0. The accelerations are 0. Let's see. At about, say, 2 seconds, I mean, the accelerations are more, it's increasing. Then after that, we'll have more accelerations. Okay, so we'll get more response after, say, about 2 seconds. Let's go to the results. Okay, so for each time cycles, we have the results. Okay, we can see the minimum maximum values. Okay, so let's see the deformations first, how it is deflecting, how it is dancing to the tune of ground shaking. Relative displacement, total deformation, say it's like this. So for the deformation, what we have to do, we have to first set up this. Okay, I don't want minimum, maximum, absolute, this is fine. And this multi-mode animation recording I have to do. Okay, and here I can have auto range. Okay, and then for multi-mode range, let's start the animation. So you can see the time steps here. Okay, and see this is not the correct animation as of now. It is, the software is rendering. Okay, so once this rendering is complete up to all the time steps, then you will have the actual animations, actual deformations. Okay, still this is not correct. In the initial time cycles, it will not deflect the way it is deflecting now. Okay, just wait so that this rendering, animation rendering, is complete. Okay, so after see, we are just for visualization purpose, we'll check its behavior. Then we'll compile the reactions, vertical and lateral reactions at the at supports, and then I'll take it to the Excel sheet. There I'll paste it there, and then we will plot factor of safety against sliding versus time period, and we'll check the absolute values of I mean the minimum and maximum values of the principal stresses in the founding block at the foundation, and normal stresses in the interface element to check how much okay, now it has started the actual animation. So still we are at 0.3 seconds. So it's the deflection is not, I mean, you cannot view the deflection. Deflection is not significant. So at about 2 seconds, it will start vibrating more. So it will go on increasing. Okay. So it has started deflecting more now. Okay. And look at the deformation bulb. So deformation is restricted in this location itself, prime major deformation. So this color is 0 actually. So whatever we have modeled, this should provide a, I mean, the desirable response. So, okay, so it's about 3.5 seconds. It is, I mean, it is deflecting more now. So, I mean, it is as per the acceleration value at the acceleration of the ground motion. Okay, so up till 8 second we'll get the maximum deformation. So this deformation seems fine. Okay, let's stop it. And now what we'll do, we'll okay, undeformed, we'll get the reactions, extract. So there's a lot of data. It will take some time to get that. I mean, the software will take some time to get that, to process that data. dB, then reactions we want in say horizontal force. First we require Tx, and we want up to 800 cycles only. We don't want minimum maximum. For each cycle I'll check the factor of safety, and then select the nodes, select all the bottom nodes where you have applied, where we have applied the restraint, and table. Again, it will take some time to for the table. Now this was the earlier data. Maybe I can delete this to here. So I have this function with me. Probably I can include few lines here, insert few columns here. So my data can be, I mean, more. Let's see. So yeah, so I can have insert, so that, I mean, this sum total now, I mean, these all the curves are linked with this sum, so I don't want to do it again. That's why I just want to, I mean, manage my data within these cells behind those sum total. Okay, so I'll be using this to some extent now. Probably, let's see. Yes, it has. Now I can copy this data, select it. Again, it will take some time for selection. So when the color changes, that means it has selected. Right click, wait for some time again. this pop-up menu will appear. Copy, wait again. So till you get a message here, 800 rows have been copied. Now it has been copied, then paste it here. You can create your own sheets. I mean, where is A? Oh, B. Let's see. Okay, so from D it is starting. This is fine. Yes, so it should work. Okay, so similarly in vertical also, just take it up to here. Okay, so include some rows here, columns here, and click save for. There should be enough columns. Those are included so that I can manage my data here, close it. Okay, now for the same nodes I need TZ reactions. Okay, table. So it will take some time. Let's wait. It's coming up. Just wait for a minute. Okay, this line appears. So now soon we'll get that table. So it is there. So select it. Again, right click. Wait for this dialog box to appear. Copy it and wait for this message to appear on the screen. And then paste it here. Vertical. Okay, let's see whether it is fine or not. Yes, this is fine. So my graphs are linked with these sum total. Okay, so that's why I did this exercise. Let's see D condition. Okay, okay, so it is fine. 1.25 is the least factor of safety, so it is fine in D condition. Let's go to E condition. For every, I mean, for as I have shown you earlier, I mean, for every cycle it has computed the factor of safeties. So if it is more than 100, then I mean more than 5, then it is not compensated here. So in most of the cycles it will be more than 5. Initially we have 0 acceleration, so in the initial cycles, I mean there's factor of safety maybe infinite also. So it is much more than that for D condition, construction stage plus earthquake. Let's see E condition, that is of more interest. Here you can see we have lesser factor of safety. Safety is 0.57. Okay, so see, and let's see how many cycles factor of safety are less than 1. So let's say I can copy paste special values and number format. Okay, I can sort it in ascending order, sort it. Okay, no, maybe I can delete this. Just sort this data, sort first smallest to largest. Okay, let's see 1, 2. Let's see how many cycles have less than 1. Out of 800, still it is less than 1. Okay, see, it is 378, almost half, 50% of the cycles the factor of safety is less than 1. This is not acceptable. Okay, so in the next session, I'll conclude this. But see, there is no such criteria mentioned in any of the code that that we should perform sliding factor of safeties for the time histories. Okay, so USC engineering manual also states that we should do it for the what you call static loads only. Pseudostatic analysis we should carry out. Let's see summary, where is that? But we were getting some negative pressures also, and let's see in E condition. So 1.22 we are getting. Okay, so this is also a bit, I mean, anyways, for 1.12 also. So this is quite close to 1. But it is more than 1. So from pseudostatic analysis, our dam is safe. But from this, if we, for each cycle, if we do it, uh, then we are getting some lower values of factor of safeties. Okay, so maybe either, I mean, either this time history data do not correspond to that alpha H values of 0.12, I mean seismic coefficient of 0.12, or if so, then more than 50%, I mean about 50% of our in time steps, we are getting less than 1 value for factor of sliding. We should actually change this dam. Okay, we'll do it in the next session. Okay, and then we will perform this test analysis. It won't take much time for optimizing it. I wanted that this dam to fail, so such that I can demonstrate that how we can optimize this dam very quickly. Okay, so okay, so this is it for this session. So see you in the next session. Thank you. In next session, we will optimize this dam. I mean, we will put some more weight on this side so that it is safe in time history analysis, factor of sliding also, and then we will perform the stress analysis. We will see the DCR ratios for certain nodes on the upstream side. Okay, and we will check the DCRs here. I mean, it should be more here because these are all flexural member. So we need reinforcement here in these nodes. Okay, we'll check here also, and we will check few nodes on the upstream face of the dam, whether the reinforcement, whether it exceeds the DCR of 1 or 2, DCR of 1 for DB case. Okay, for that we have to analyze it with the other load cases. Say for D case, we have to analyze it with the self weight. For E case, normal operating case, we have to analyze it for all the normal operating loads. Okay, we'll do it in the next session. We will conclude this in next session. Okay, so for this session, thank you very much. See you in the next session. Thank you.
Thank you, Chetan sir, for this insightful session. If you have any questions, please ask in the questions chat box regarding this today's webinar. Please ask your questions. We'll try to answer one by one. Chetan sir is with us. Like, if you like, you can ask your questions. So Chetan sir, you are not audible to us.
Okay, am I audible
Ah,
now?
yes, sir. You are
Yes,
now audible,
yeah,
sir.
yeah, 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 yeah. Yes, please
So,
ask me the
ah,
questions. Yes.
so the first question is, sir, in case of carrying out the dynamic analysis of dam for pier design, what
Huh.
should be the permissible tensile strength for concrete? If we follow the
Zero,
Raphael formula, then pier reinforcement comes
zero,
very
zero
less.
for yes. See, for evaluating reinforcement, whatever stress, method you apply, limit state, working stress, whatever. First assumption is while evaluating reinforcement, first assumption is entire tension should be taken up by the reinforcement. Piers, breast wall, trunnion beam, these are all flexural members. Okay, bending theories are applied there. We have to, evaluate the reinforcement. We have to restrict our depth of neutral axis, and for that, entire tension shall be taken by the reinforcement only. Zero tensile stress should be considered for the concrete. But there is a but here. If we are doing a numerical analysis, if we are modeling solid modeling, if we are doing, and if we are doing not doing it manually, we don't have bending moments with us. Okay, then those bending, if we try to apply those bending theories, how will we will be applying that? I mean, we don't have the depth of neutral axis for from solid elements, from solid stresses. We can restrict our this tensile strength of concrete up to 1% of FCK. Okay, say if it is 25 concrete, we can go up to 0.25. Okay, at 25 MPa from the maximum tensile stress on the outer face of the pier up to 0.25. In that particular tensile block, that particular tensile region, we can evaluate the area. Okay, then divided by the permissible tensile strength, that will give the area of the reinforcement. Okay, so this way your reinforcement, even then your reinforcement will be slightly more. I mean, if you compute it by the bending theories, considering zero tensile strength of the concrete. Okay, from solid elements, from numerical analysis, if you want to compute the reinforcement, um, consider the tensile block up to 1% of FCK.
1.1, yes. Okay.
Yes. Okay.
Okay. So next question is that we have used the Westergaard method to apply the hydrodynamic force. I think
Right.
you apply the force in the upstream to the downstream direction. In
Right.
case of reverse earthquake direction in the time history analysis, will the sign of hydrodynamic force automatically change?
See, in reverse, suction can be there, may not be there. Earthquake is such a phenomena. I mean, there are number of gray areas there. Of course, when you are considering downstream to upstream, you can have negative, hydrodynamic there. Okay, but now even Midas also has sloshing material, though I'm not very confident about the sloshing material in Midas. uh, so I'll first test it myself, then I'll be using it. So I mean, the best solution is model water itself. Let the water also behave as per the time history, as per the ground shaking. Okay, let whatever section is there, let it apply on the dam block. So in some other software it is there, probably in Midas also. I don't know if we can model the water and let the wave forms itself and let the suction applied on the dam body itself. See, Westergaard equation, that is conservative. If you consider Westergaard equation for suction or the hydrodynamic pressure, that is slightly conservative. But of course, from downstream to upstream side, yes, you can consider suction with the negative symbol. I mean,
Hmm.
with the Westergaard equation. Yes, but best is just model water. Let the
Hmm.
software, yeah, form the wave. That way you will
Hmm.
get the best response.
Yes, that's why we added the sloshing fluids in this Midas version right now. Okay,
Yeah,
you can check it. You can first check out that according to us it is working properly. But if you
okay.
want to check it, you can check, sir.
Yeah,
Are you still streaming? Yes, sir. We are still streaming. Kamal, sir, we are still streaming. Anyone, have different questions? Please ask. Any questions from the audience? Please ask. Yeah, two questions. I think that's all for today, sir. We have not received more questions. The 2, 3 questions are there. We already answered them. So thank you, sir, for these insightful sessions. Like these are very good sessions. I am also attending it. Like, yeah. So yes, one person asked, permissible stress of concrete for different load case are given in 6512.
Hmm.
Why not we use that?
See, IS 6512 and other codes, those codes were prepared when we didn't have the software with us. IS 6512 is of 1984, and other codes also. At that time, we had to do it analytically, manually. Okay. Uh, See, all those zero point 0.01 FCK or zero point 0.02 FCK for different OT conditions, those are for analytical purpose also. See, at different levels we can evaluate the stresses. Different level on the upstream face of dam, we can evaluate the stresses, I mean, as per the applied hydrostatic force. And but at different levels, how to apply the uplift force, that also has been given in the code in 2200, or also it is mentioned in our Indian code for the PA design. It is also mentioned that you can apply the this uplift at different levels. It's, I think, 50%, and then you can reduce it on the downstream side to zero level at a different level. But those all things, all criteria are for the analytical solutions, for manual computations. If we try to restrict it zero point 0.01 FCK here for earthquake condition on the upstream side, or zero point 0.02 FCK, you will never get that, because on the upstream side, there is no node on the upstream face of that. You can get that, but then the dam section will be uneconomical. There is no node on the upstream side of the upstream face dam nodes, so there can be some singularity there. So some minor tension will be there in some of the nodes in on the upstream face of dam, 0.003 or 0.0001. Okay, but that doesn't mean that our dam is not correct, because it is not abiding by the IS 6512 stresses. So those stresses, those criteria are more applicable for the analytical solutions. Our code should be modified as per the latest technologies. We are not living in 1984. Okay, I at least follow USAC Engineering Manual 6051, which is in, I think, 2003 it was updated. Okay, so we are not living in 1984. We should, I mean, modify these codes now. It's time to modify these codes. We are modeling
Mm,
water now. Yes, so we are
mm.
moved much ahead of those times.
Yes, sir. Yes, sir.
Yeah.
So one of the user asked us, sir, should the reaction in XZ direction be checked at the bottom of the rock mass or at the dam foundation level?
See, dam foundation or rock, we have not inputted any density to the rock. Whether you Wherever you have applied the restraint, you have to check the reactions there only. Software will provide reaction only at the supports. Okay, grid forces it will give on at every place. But here, if you check the, I mean, here the reactions, here the supports are provided at the bottom of the ground. So reactions will be at the bottom of the ground only. So
Mm,
in earlier, when I was doing a rigid base analysis, okay, when I
mm,
had not modeled the foundation, then I applied the supports at the founding level of the concrete dam. Then I have to check the reactions at the founding level itself. So wherever you apply
mm.
supports, you check the reactions there only.
Okay, sir. Thank you. Thank you. So one of the user is asking to make a video on topic of enforcement calculation from the solid stresses from Midas. We will definitely do
Okay.
it, sir. We will
Yeah, maybe next
definitely,
yeah,
yes,
sometime later, maybe. Yes.
later. Yes, sir. Yes, sir. We will cover.
Mm.
Yeah, sir. So I think that's it for the questions, sir. Thank you for these insightful sessions. Like these are very good sessions. I really enjoying it. Like because like you showed us what the USAC manual suggests regarding these dynamic analysis, when we have to use this relic damping, when we don't have to use this relic damping. These are some sort of confusions which are like currently facing by the new engineers, including me also. Okay, so that session is very good, sir. And I'm also thanking my audience to attending these sessions. And like we have last sessions tomorrow. Okay, so please attend it, in which we will cover the crack propagations by using smeared crack material model. Okay, so please be with us for the next session also. Thank you, sir. Thank you, Chetan, sir, for these sessions. Thank you.
Thank you. Thank you.
Thank you. Okay. Bye-bye, sir. Bye-bye, audience. Please join us tomorrow.